Thanks. So this is based on a joint work with two Yuvals, Yuval Dagan and his advisor Yuval Filmus, and Yechiel Lee, who is my current PhD student. Right, so I'm going to talk about some problems in complexity theory, in particular communication complexity. And they say that the first slide of a good math talk should be accessible to general public. But I'm going to put some technical things here on this first slide. But I'm going to break this rule. But I promise the next slide will be easy. So this is mainly, I'm going to say what kind of problems I'm going to talk about in this talk for people who know the notation. But then I'm going to step back and define those notations. So it will be something in the two-party communication model for those who are familiar with this. And the main question is that when you allow an error of epsilon, how much you can save in communication complexity compared to the case where you're not allowing any error. And so in particular, if you're familiar with this notation, I'm interested in the asymptotics of this difference, the zero error versus the epsilon error when there's an underlying distribution mu. And a more concrete example would be, for example, for the AND function, just the 2-bit AND function. So you have two players. One has one bit, the other one has another bit. They want to see what is the AND of those. In one case, they don't want to make any mistakes. The other case, with probability epsilon, they're allowed to make a mistake. And we're interested in the behavior of this thing with respect to epsilon. And if you've worked in communication complexity, probably similar to me, you've developed this bad habit that you don't care about constants. But once you move to information complexity, constants become important. And in particular, like for something like AND function, it makes sense to actually study what is this information complexity. And this is a constant. And it's computed very recently in this really nice work by Braverman and Ankit, Denise, and Omri. And it has really interesting applications, which I'm going to get to. OK, so yeah. For example, what is this asymptotics now if we allow epsilon error? So now the much anticipated second slide is that, all right, so what is information complexity? It's just a continuation of Shannon's information theory. And it's really a recent area. And I find it really beautiful, many of these results in this area. So what is Shannon's setting? We have two players, Alice and Bob. So this is Alice, say this bald one is Bob. And there's a one-way channel. And what they want to do is, so Alice is receiving many samples from a single random variable x. So these are just getting samples, and these are independent samples. So they have the same distribution, but they're independent. Now she wants to transmit this to Bob. So she wants to send one message from which Bob is supposed to recover this x1 to xn. And with some small probability, let's say, he might say, I can't recover, or he might recover something wrong. And the question is, how many bits does she need to send on average as n grows, so asymptotics with respect to n? And this important theorem of Shannon, which is known as Shannon's source coding theorem, says that if you take this number of bits divided by n, as n grows, this converges to the so-called entropy of the random variable x, which has a nice formula. And from this, you can say, in a sense, that this entropy really captures the essence of this random variable. How many bits of information is inherently there in this random variable x? And you really see this when you go to this kind of amortized way, that you have many copies. If you just have, say, one bit, it's hard to really get this kind of algorithmic meaning for it. Like you just get a formula, but it doesn't really mean much. But once you have this amortized way of looking at it, the entropy really comes out of it naturally. All right, so that's Shannon's setting. Now, in Shannon's setting, Bob is quite passive, right? He's just sitting there waiting to get this message and decode it. Now, in communication complexity, they're allowed to interact. So Alice sends a message, Bob sends something back. And let's say we have a distribution on these inputs. So let me say, what is this communication complexity model, the standard one? So let's say Alice receives a random variable x, the input x. Bob receives a random variable y. And they're sampled from some joint distribution y. So they're not necessarily independent. They can be always the same, or with some probability the same, and so on. So there can be some correlations there. And now what they want to do is they want to compute some function. And they want to collaborate to do that. For example, they want to see whether these two inputs are the same or not, the equality function. one of the important functions in communication complexity. And now, how many bits do they need to really communicate to do this task, to compute this value of the function f, to see whether their inputs are the same or not, for example? And that's the setting of communication complexity. So there are two main tasks, communication tasks, that are often studied. So let me define these, and we'll work with these in this talk. So we have a communication protocol which says how they're going to interact and what they're going to output. So let's denote that by pi. And this pi has access to randomness. So these Alice and Bob, they can flip coins, and according to which decide what to do, which message to send, and so on. And in the first task that I'm interested in, which I'll denote it by f and epsilon, what they want to achieve is that for every x and y, every single possibility of x and y, the probability that something goes wrong is at most epsilon. So this is independent of the distribution of x and y. Every single x and y that you pick, you want to achieve this. So this probability, the randomness in this probability, is really coming from this randomness in the protocol, the coins that Alice and Bob are tossing, not from the input. The input is for every x and y. The second one task is the distributional task, which I'll put this mu here to say that in addition to the randomness in pi, now we also sample the inputs randomly. So x and y are also sampled according to some distribution mu, and now what I care is that, okay, so if you sample this input randomly and then you run your random protocol, what is the probability that an error happens? So in the second task, this is what I'm interested in. And of course, this is an easier task compared to this one, right, for every mu. If you can do this, of course, you can do this for every mu. Now, the common notation in communication complexity is that the communication complexity of the first task is often denoted by this r epsilon of f, the randomized communication of f. The second one is this distributional, it's d mu epsilon of f. But I'm going to stick to this notation, cc, standing for communication complexity of these two tasks. All right, so that's these two tasks, and a simple minimax theorem, which appears in Yao's important paper, which kind of initiated this area, says that this one is, it's of course an upper bound for every single one of these things, but there exists a mu which actually gives you exactly this, the communication complexity of this first task. So this, there is a difficult mu, the most difficult mu, which actually is as hard as doing it for every single input. All right, so that's the min-max theorem. Now, something more recent, information complexity. So here, this is an extension of Shannon's information theory, and it's in the setting of communication complexity. So the setting is exactly the same. They want to collaboratively compute this f of x, y. But now they don't care about the amount of information. So they can talk as much as they want, exchange as many bits as they want. But what we are interested in is how much information they are revealing by communicating. So it's this thing that is called information cost. So as they communicate, they learn more about each other's input, right? Initially, Alice has x, Bob has y. They might be independent, so in that case, they don't know anything about each other's input. But as they communicate, slowly they start learning things from each other's input. And we want to minimize that. And we can measure that using entropy, right? It's how we measure information. So the exact definition is here, but it really doesn't matter for this talk. You can completely ignore it. If you're familiar with these things, yeah, so that's the definition, but you might as well ignore it for this talk. So information cost of a protocol is really how much Alice learns about Bob's input plus how much Bob learns about Alice's input from the communications, measured by this mutual information formula, this addition. And to be able to talk about information, you need to have a distribution mu. This distribution mu is what gives you some information content to these random variables, right? Right. So it's obviously upper bounded by the sum of the entropies of x and y, but it can be much smaller or close to that. All right. So I'm going to denote that with this thing, information cost of pi with respect to measure mu. All right. So now if you have a communication task, of course, you can say how much do you need to pay in terms of communication costs to be able to perform this task? So that would be the infimum over all protocols that perform this task. So you look at their information costs of all of them, and you take the infimum. And here, you can't take the minimum. Infimum is necessary. Even for something simple as the AND function, you can have, you really don't have a single protocol which achieves it. You can construct a sequence of those that achieves it. All right, so that's the information cost of a task. And of course, the two tasks that I said we're mostly interested are this one, f epsilon and f nu epsilon, where now I'm measuring information error with respect to nu, and measuring information with respect to mu. So these two don't necessarily have to be the same thing. So here I'm interested in computing f, where if I sample inputs according to this distribution nu, I have an epsilon chance of making an error, but I'm measuring information with respect to mu. So that's a different thing. That's how I measure the information. All right, so we have these two things. Now, so remember Shannon's theorem that when you look at amortized costs of this transmission, it corresponded to entropy. And there's this beautiful theorem by Braverman and Rao from 2010, which says something very similar is happening here. Now, let's look at this task of computing f with distributional error epsilon. Now, suppose you want to do that n copies of the same task. So Alice gets n inputs x1 to xn, Bob gets n inputs y1 to yn, where every pair is drawn from the same distribution mu independently. And now they want to communicate and solve all these problems at the same time, so that for each single one of them, the probability that they're making an error is at most epsilon. And if you look at the communication costs of this is not the information, it's just communication. In the amortized sense, when you divide it by n, it converges to the information cost. So it's a really beautiful theorem. It says, okay, again, the same thing. This essence of this communication is captured by this information. And you see it when you look at it in an amortized way, how you do it in simultaneous way, solving all of them. And this is for epsilon larger than 0. For 0, it's still a mystery. We don't know exactly. And there's another one, which now, let's look at this task. So this is a paper later by Braverman, which showed that for this one, you converge to the following thing. Now what I'll get is that I'll pick the hardest distribution mu and look at the information costs of computing this task. So computing f correctly on all the inputs with error at most epsilon. And a simple min-max argument shows that I can write it in this form, that now I look at the hardest distribution mu in terms of information and hardest distribution nu for the error, and look at computing this, performing this task of computing f with distributional error nu at most epsilon. I haven't seen really this written anywhere, but I'm pretty sure it's known to people. So it's a simple observation, basically. But it's kind of, from this, it's easy to see how these two things relate, really. Okay, so we have these two observations they wrote, or theorems, not really observations, they're really both great theorems that's written up there. Now, from those, kind of Braverman defined the following. So if you look at those, you would want to define the following thing, which is prior free information complexity, which is, let's look at the hardest distributions and see what is the lower bound we can get for the information. And these are good for obtaining lower bounds for communication complexity. So one is just looking at this one, the second one. Let's call that prior free information complexity of f. There's no distribution here. It's really for f and epsilon, right? Because both distributions are maximized here. And now also you can look at the first one here and look at the hardest mu. So you can maximize that. And Braverman called that distributional prior free information cost of f and epsilon. Yes?
I'm sorry, could you remind us, so mu and nu, what are the two?
So nu is the error. So you sample the inputs from nu, and you want the probability that you're making an error is at most epsilon when you do that. Now, mu is something that comes when you're measuring the information cost, right? Okay. All right, so from this, so here we have the same thing. Now, obviously, by looking at this, you see that this is a lower bound for this one, right? Because here, these two have to be the same. Here, they're free to be anything. But what Braverman observed is that proved. So this first one is not that difficult. That if you don't allow any error, so when your epsilon is 0, these two things are the same. But when you allow error, so when you have epsilon larger than 0, they are roughly equivalent. What you get is that, as I said, this one is obvious. But what he showed is that you can upper bound this one if you're willing to decrease your epsilon by a little bit. So you're multiplying it by some alpha, which is less than 1. Also, you're multiplying this whole thing by a constant slightly larger than 1. So you're paying in both ways. So a larger than 1 constant here, and you're decreasing the error. But it's not that bad. Say if you take alpha to be half, you get 2 here, and you get epsilon over 2 here. So that's what he proved. It's a really interesting proof. And what he asked after that as an open problem is that, are they actually equal? So it might as well be the case that for every epsilon, these two things are equal. It's not just 0. So that was one of the questions in that paper. And as I'll mention later in this talk, we showed no, they are not the same. And right.
So just understand.
Yeah.
So you're asking, is it when I measure my error with respect to a distribution, is it always sort of good to measure also my information?
Yeah, with respect to the same. Yeah, exactly. Right. So the counterexample will be set disjointness, which is really the probably most important function in communication complexity. So in this problem, Alice and Bob receive 2 sets. They want to know whether they intersect or not. Right? So if there is no intersection, let's say the output is 1. If there is some intersection, the output is 0. And this is, so people worked on trying to prove lower bounds for this, and it was really in early 90s that finally it was shown that you really need linear number of bits to communicate, and there was a short proof by Sasha, which is short but not very easy, which shows, yeah, exactly. So you get the lower bound, but in this sense, which is usually what people are happy to have in communication complexity. Don't care much about the constants. Right, so we have this theorem from 90s. And one thing about this function, disjointness, is that it's really nothing but OR of ANDs. Right? If you encode these 2 sets as just vectors, 0, 1 valued vectors, what you want to compute is you look at all these ANDs. These ANDs correspond to intersection, right? If they're 1 if an element I is in both x and y. So if something is like that, you get a 1 here. And then you're taking the OR of those. So that's really the intersection. I have to negate it to get disjointness, right? So you have this nice structure. But that kind of rings a bell that this really looks like an amortized AND, right? So you want to really compute a lot of ANDs at the same time. So maybe something related to those amortized results. And in fact, yeah, in this paper of Braverman and his co-authors, they use these ideas together with some previous things that come from previous sources. This is a really long paper. It's a lot of ideas in the theorems. They managed to prove the following. They managed to nail down the exact constant as epsilon goes to 0. So let's look at the communication complexity of computing disjointness. As I said, it was already pretty hard to show that this is linear. But they managed to show that as epsilon goes to 0, you get this constant. So you're converging to this 0.4827n plus this little of n. And this constant is really coming from the AND function. What is this constant? It's the communication information cost of computing the 2-bit AND function with no error, 0 error. But also, you're only interested in measures who are supported on everything but this point, 1, 1. So mu of 1, 1 has to be 0. So out of the 4 points, your measure is supported on at most the other 3, 1, 0, 0, 1, and 0, 0. So you kind of cross off this from your measure. And if you look at those distributions, you can find out which one is the hardest and compute this thing. So this is really the heart of this paper. It's really not easy to compute, even for this 2-bit function, what is the exact information cost. So you get this constant, and that's really what's happening there. Right, and then they asked the following 2 questions in the paper. That right, so this is true when epsilon goes to 0. What if we care about the rate of convergence? So what if epsilon is some other small constant? How big this thing is, or how big this one is for disjointness? And the same question for communication complexity. How does it behave if you actually want to have an epsilon here, and not just a limit? And yeah, so we looked at these questions, and they're kind of all related to each other. So so one of our main theorems is that this is really of the order of entropy of epsilon, which is epsilon log epsilon. Right? So if you look at the AND function, the information complexity of AND function, 0 error versus epsilon error, asymptotically this is equivalent to h epsilon. So the amount you gain is the entropy of epsilon. And the same thing for disjointness and communication complexity of disjointness. So this constant that we had previously there, you can decrease it by something which is asymptotically of the order h epsilon if you're allowing this error epsilon. And these are not easy theorems. So the upper bound is fun and easy. So you kind of play with and you come up with a nice protocol and it gains h epsilon. But proving lower bound was quite hard for this one. So we tried to generalize the methods that they had. And in theory, you can generalize the framework, but then you can't really apply it. And one thing is that for 0 error, there's this buzzer protocol, which we know it's optimal. But for epsilon error, we don't have any conjecture what is the optimal protocol. And if you don't know what is the optimal protocol, you can't really work with their framework, which is checking these like local convexity conditions. And I think in this case, even if you know what is the protocol, it wouldn't be easy to check that because you'll have so many other variables. All right, so for a while we were working with this, but then in the end we took a completely different approach. We proved some stability results, and from that we managed to get this result. But it's like at least 10 pages of proof to just get this simple, like for AND function really. All right, and the other thing we did was we looked at disjointness function, and now in this other prior free thing, so distributional prior free. So now I give you a distribution mu, and you want to upper bound this one. And interestingly, here you can save more. You can save, instead of h epsilon, square root of h epsilon. But you're paying this log n here, which doesn't matter much if n is big compared to epsilon. So you gain more here, and this is the same constant as before. Right, so this is how we separated those prior free and distributional prior free quantities, questions of Braverman. So from this, right, so it shows that for disjointness, these two things are not the same. And in fact, we get more, that actually Braverman's inequality is sharp. Not only these two things are not equal, also in addition to that is that just the analysis that he had, that inequality with alpha is sharp. With the right value of alpha, you cannot even improve that inequality. Which was quite interesting because, I mean, that inequality didn't seem to, in the beginning, it would be something that's sharp. It's just something that came out of the proof. All right, okay, so for this one, right, so this is an upper bound, and it's fun again because you need to come up with a protocol which does that. And the way we get this upper bound is the following. So you take a random order of the bits, so from take a permutation of 1 to n, and you do the following. So you try to compute these AND functions one by one, starting from the beginning. And if you find an intersection, you're done, right? If you find an element which both of you have it, you're done. So that's your goal. You'll stop at that moment. So what you do is, to compute the AND function of this, you run a protocol which comes from this analysis of the AND function that has this much error, where p is this quantity. But also, you only allow one-sided error. This one arrow to 0 means that if the AND is 0, you don't want to make a mistake. You don't want to miss that. So your protocol is not allowed to make an error there. But if the AND is 1, if both your bit and Alice and Bob's bit are 1, they might make a mistake with this probability. So it's really important that it's one-sided. Otherwise, you wouldn't get a protocol. So you get something like this. And then you care about also how you're measuring these information costs. So these are the marginals conditioned on some events. So then, I mean, this is the protocol. Then you have to analyze it. And the analysis is like a 2-page. It's not that bad. And out of that, you get this kind of nice upper bound. Right? So it's coming from that. All right. OK, so let me jump to open problems. I think this is a really nice open problem. It's really about, again, nailing down the exact constant. So our proofs show the following thing. Shows that, so let's look at the computing disjointness function with epsilon error. Look at information cost, or if you want, you can look at the communication cost. So R epsilon, doesn't matter. If you divide that by n, it's not that hard to show that that's lower bounded by this thing. Computing the AND function with epsilon error, the information cost with those particular distributions that don't put any mass on 1, 1. Right? So you get this lower bound here. But now, let's move to one-sided error. So now I'm interested in the same thing, but more restrictively. So now I don't want you to make an error if there is no intersection. So this, again, means that if the output is 0, you're not making an error. The only error that you're allowed is that changing the output 1 to 0. So that's one-sided error. Of course, if you add this restriction, you're increasing the information cost, right? So you get this. And now you can upper bound this by the previous kind of protocol, similar to what I had in the previous slide, by computing the AND function one-sided error, right? So you have this kind of, these two things are sandwiched between these two things. And the good thing is that whether you'd want to do with one-sided or two-sided, you still have the H epsilon error. So that's how we get this H epsilon gain and solving their conjecture. But what it seems to be true, which right as a conjecture, is that this thing is really, this seems to be the right constant for both of them. So maybe we can put this even in the lower bound here. So that would be really interesting, right? So that would tell us that the information cost of this disjointness with epsilon error, again, as I said, you might as well write here R epsilon of disjointness. So it's really, if you're just interested in communication complexity. Asymptotically converges to this constant. So this constant times n, that's the right asymptotic. Now what this constant is probably hard to compute. We might not be able to compute it easily. But it is a nice meaning, right? You're just computing the AND function with one-sided error, epsilon error. So this would be nailing down the exact constant for the communication cost of disjointness when you have epsilon error. All right, so yeah, okay. One other open problem, so I thought I would run out of time, but I put it as a backup plan, is that, so what we proved is more general. It's really not about AND function, is that indeed, for every function f, you gain H epsilon. So the upper bound is true for every function f. So when you're allowing epsilon error, you gain H epsilon. But for the lower bound, what we managed to prove in the general case is only square root H epsilon. And this is as epsilon goes to 0. And it seems that maybe the upper bound is always true. Maybe what we saw for the AND function is in general true. So definitely we can prove equality here if mu is of full support. So the trouble here are weird measures which are not of full support, and their support is very very restricted. So they're kind of abnormal kind of measures, but there might be a counterexample there. So we can't really prove a lower bound of H epsilon there. All right, so that's another open problem. I think I'll stop here. Thanks.
I have a question. So you had this example for the end function where this sort of quadratic gap with distribution without distribution, right?
For disjointness.
But this is for the end function, right? So the information correctly for the end function.
No, the quadratic gap was disjointness, right? This H epsilon, this one. Right. This is disjointness, and this is a bit different because this is not really about epsilon goes to 0 compared to n, because I have this additive error here. So the other things are really like you fix n and then you let your epsilon goes to 0, like you're interested in that. So this is really not a counterexample to the last open problem. Yeah.
No more question. Let's come again.
Thanks.